I would like to start the session, keynote session. I'm the Takayama out of Nagoya University, and I'll be chairing this keynote session. Today, we have a very prestigious speaker, Professor Tomoaki Ohtsuki. Let me briefly introduce to you. He was the past president of IEICE Communication Society, this society, and he was the general co-chair of the last year's ICETC 2020. And I would like to mention one thing. He is the one who started this conference. So without him, we don't have this kind of meeting. And the one more thing I would like to mention, he was selected in the 7th edition of 2021 ranking of top scientists in the field of computer science and electronics. I will give you the link. So, ladies and gentlemen, please welcome Professor Tomoaki Ohtsuki, and he will talk about the, let me see, I forgot the title.
It's okay.
Machine learning for intelligent wireless communications. So please welcome Professor Ohtsuki.
Yeah, thank you very much. So, Professor Yamato, yeah, thank you very much. So, okay, let's start with, okay, I hope you can see this one. Okay, so thank you very much again. So Professor Yamada also thank you very much everyone. So to attend this my keynote. So as Professor Yamada introduced, so I'm one of the co-founder of this conference. So it's my great honor to give a keynote speech at this ICTC. Okay, so yeah, I checked the attendees' names. So I found that some of you are more familiar with this topic, but yeah, I tried. So the title is today is Machine Learning for Intelligent Wireless Communications. I'm Tomoaki Ohtsuki from Keio University, Japan. So actually today, so some part of my presentation, so some of you have already seen before, but I try to include some new ones. So I hope you can get some information. Okay, so let's start with the 6G. So the 6th generation wireless communication or cellular communication systems. So, well, I cannot see, just a moment. So probably, so many of you talking about or doing research about 6G or beyond 5G. In 6G, as you know, so we are targeting very high performance, even compared with 5G. So this is a very popular, a figure. So you can see various axes, so represent each performance. So the light blue color represents the obtained by 5G, and the blue one is by 6G, so around 2030. So for example, yeah, peak data rate, yeah, it's up to about 1 terabps, even at 5G, 50 times. And also for example, the connection density, 10 times compared with 5G, and also the air latency 1/10, even compared with 5G. Oops. Okay. So, of course, these are very challenging. So there are many techniques we need to use to achieve this kind of the very high performance. So this is the one that I pick up from the white paper by Nokia. So 6 key technologies for 6G. So yeah, so many companies, so they published a white paper, and some are very common. So but let's see For example, the first one, AI ML-driven AI interface design and optimization, expansion into new spectrum bands and new cognitive spectrum sharing method, and also the integration of localization and sensing capabilities into the system definition. And also this one already mentioned the extreme performance requirements, particularly latency. Also, I didn't mention battery reliability as well. Also, the network architecture paradigm involving the subnetworks and rank-core convergence, and also the new security and the privacy scheme. So, as I picked up our listed first, so AI, ML, expected to play a great role, even for 6G. So this is a figure I like. So we can say AI is one of the key enablers of 6G. So yeah, of course, AI, it needs a big data, but not only just AI or big data, of course, conventional or traditional theory, like signal processing, communication theory, and others, of course, needed. We need to combine and set up a new theory or new system. Okay, so let's talk about the deep learning-based wireless communications. In this talk, I'm mainly focusing on the physical layer, so I will introduce some examples. Okay, so why deep learning or why AI? As you know, so wireless communication systems are becoming more complex, and also the amplifier or some others, it contains many imperfections and also the non-linearity. So it's very difficult to approximate accurately. Then if the approximation or modeling is not so good, then some theory based on it doesn't work well. That's a challenging part. But if we use, for example, deep learning-based communication systems, so in many cases, so those do not require mathematically tractable model, but still be able to achieve the better performance. That's why many people are talking about deep learning or AI in even a wireless communication system. And also the conventional block-based optimization, as I mentioned here, does not always provide the best possible end-to-end performance. And also the joint optimization of the signal processing blocks is often computationally prohibitive. And not always, but so some techniques around end-to-end optimization may be able to provide a superior performance. That's also one of the reasons why people are talking about AI or ML in wireless communications. Okay, so DL-based wireless communications. So people are doing research a lot in various aspects, various layers. Physical layer, dendritic layer, network layer, even a network or network security, and also some analysis like network level mobile data analysis and up-level mobile data analysis. So as I mentioned before, so I mainly focus on the physical layer. So mainly that is the signal processing. Even just for the physical layer, there are many works going on or already done. So for example, our team also did some work about the modulation classification, error correction, interference management, MIMO detection, MIMO precoding, channel estimation, noise estimation, and so on. There are many. So the first, I will pick up the AutoEncoder. So how to apply the AutoEncoder to the communication system. So like this one, we model the communication system as an autoencoder like this one. So here encoder part, this one is a decoder part. Usually encoder, so our autoencoder, so we can use it to find a useful representation of the Y of X at an intermediate layer. So then we can say, or we can use this one, for example, as a feature selection method. And we can say, for example, that we can model the transmitter like this one, and also the receiver, and the intermediate, this part as we can say the channel. Well, here the picture or figure that I picked up from this paper, early paper about the modeling the communication system as autoencoder, like this. So transmitter part, channel part, and the receiver part. So I don't go into detail, but you can easily find or understand this one. So let's see the performance of this kind of the system. So this is an example of broken rate performance of the autoencoder modeling system. So here, so broken rate performance versus E sub B over N0. So the code rate is 4/7. So this one uncoded BPSK4 case, and this blue dotted line represents the performance of the Hamming 7/4 hard decision one. And this blue dotted line represents the Hamming 7/4, but with MLD. And the interesting thing that we can see in this figure is autoencoder type 7/4. It achieves the same, almost the same performance as Hamming with MLD. That means that autoencoder, well, it needs training, but the autoencoder has run without any prior knowledge of encoder and decoder function and kind of the error correction ability. That's very interesting one. Okay, so regarding the 6G, so the massive MIMO also the expected play one of the great role. Also the first keynote today, also the Professor Rappaport also mentioned. This is a very important technique. Massive MIMO, as the name mentions, so it equipped with a large, very large number of antenna arrays, particularly at the base station side. And using those kind of the very large number of antenna arrays, we can make the beam very narrow, a sharp beam. That means that we can improve the spatial use, that is the spatial efficiency. That's why we can expect a significantly increased spectral efficiency. That's why the massive MIMO is expected to play a great role in 5G, 6G. Well, maybe 5G, latter part of 5G. But of course, if the number of users increases, detection of a large number of streams is required. So it is also a challenge. Why? Because of the complexity. So there are many research, also there are many algorithms so proposed for massive MIMO detection or MIMO detection. So like a map detection or spatial filtering, like MMSE or zero forcing, or QR decomposition-based algorithm, and also the detection based on brief propagation algorithm. So if we see the complexity order, so by using the number of antennas, also the symbol constellation size, for example, this spatial filtering, QR decomposition, these popular techniques, so the order is proportional to the n cube. So because the massive MIMO n is large, so then it becomes very, it results in a high computational complexity that we have to worry about it. So on the other hand, so this one, detection-based BP algorithm, so the order is low, like n squared. So that's why not it doesn't achieve the best performance, but reasonable performance with lower complexity. That's why including us, so some people are doing research about the detection based on BP. Okay, let me briefly explain the MIMO BP detection. Probably some of you are more familiar with this one, but I try to give some some information about this one. So this is a factor graph representation about the MIMO detection. So this side is symbol nodes, this side represents the observation nodes. So between the symbol nodes and observation nodes, information are exchanged and updated, and then try to get a good detection performance. The information, that is the a priori information from symbol node side to observation node side, and also the a posteriori information is the opposite direction. Yeah, like this way. So related to the, so we can say this is a kind of iterative process. So I mentioned here the iteration. So related to iteration, so one of the interesting technique and important technique is deep unfolding. So so proposed very early, not very early, but 2014. The idea is like this. So they unfold the iteration into a layer-wise structure analogous to a neural network. And then decouple the model parameters across layers to obtain novel neural network-like architectures that can easily be trained discriminatively using gradient-based method, like this figure. So let's see the similarities between a BP factor graph and also the DNN, deep neural network. Nodes and neurons transmitted signals and input data, receive signals, output data, and also the else iteration, else hidden layer. So this is unfolding part particularly. And with messages, hidden signals, and the message updating rules, message function between layers, and correction factor and parameters. So like this one. So unfold the iteration into this. So this iteration corresponds to this kind of the hidden layers. So this represents the structure of the DNA detector with 2 BP iteration. So let's see the performance of this kind of technique. So this represents a PR performance versus average received SNR for 8x32 MIMO case in IID lazy channels. And other parameters also you can find in this paper, but so see the performance. So this one is the performance of DNN based one. So yeah, for example, this one is MMC and others also that they mentioned here. So you can see this one achieves a very good performance. So as I mentioned, so the complexity is, well, so not so high. So then it's good. But we have to worry about something. For example, the suboptimality of BP detection. So if you are familiar with, for example, the LDPC code or BP detection or BP algorithm, then you know the loop, the effects of loops, or particularly short loop. Unfortunately, MIMO channel matrix has a loop. So that's why it doesn't guarantee to convert to the map. And also the antenna correlation can aggravate the looping effect due to loss randomness. So this kind of the looping effect, you have to worry about it. There are many researches to solve the effect of degradation by the looping effect. And also that we developed and published in even also the IEICE transaction many years ago. But this is one dumped BP detector. So in the updating the information, so then as you can see, using the damping factor, so it controls. Then so try to reduce the effect of the loop, then try to improve the performance. And related to this one, we propose and presented the technique. So BP detector with node selection and damping factor learning. So you can find the information in this paper, but I will briefly introduce this technique. Yeah, node selection itself already exists. So before us, for example, the proposed by Ogawa sensei and Ogane sensei, the group, Hokkaido University group. So node selection, so it updates not all, but some of the observation node with low correlation in one iteration, like this one. So you can see not all nodes in blue. Then in each iteration, so in DNA unfolding part, so we can see in each hidden layer, so some doesn't connect. So then by using this one, we can reduce the effect of short loops, or we can reduce the short loops, and we can expect the improvement of the performance. Okay, so let's see the performance. So this one, well, the bit hard case, that is a 16 by 16. So that's why we can see the error floor, but let's see the performance, BR performance versus SNR. This blue line represents the BR performance without a node selection. And this red line represents BR with node selection. And this one, the best one is a node selection with, as the title mentioned, damping factor lining. Damping factor, as I mentioned, so we control the updating of the probability or message by this factor. So we want to, how can I say, optimization is difficult, but appropriately set up to improve the performance. But it's challenging. Then in our case, so we apply the deep learning technique to learn this damping factor. And also, even in many wireless channels, so we want to use it. But every case, for example, every correlation parameter, if we need to learn, then it costs. But if we use the node selection technique, then if we learn uncorrelated case, then use this damping factor for uncorrelated case, it works. That's why this achieves almost the same performance. So this is one of the results that related to BP and deep learning. Okay, let's see the other technique. For this one, so as mentioned here, this is the image illustration, very popular one in like, I don't know, not a computer vision, but or vision or other field. So like this, we want to restore the image. So usually, so as mentioned here, so based on the training data, so the image is restored. But one of the interesting technique is deep image prior. So as I mentioned here, contrary to the belief that learning is necessary for building good image priors, a great deal of image statistics is captured by the structure of convolutional image generator independent of learning. So it may be hard to see this is the ground truth. And this is trained one. So then with training data, of course, it achieves a good performance. But this one, not trained one, non-training one, but still you can see the very good performance. So this comes from the, according to the paper, then comes from the structure of the convolutional image generator. That's very interesting. So maybe in this field, so already very popular, but in communication field, so it's not so. So algorithm is like this. So the input, of course, we don't need, in this technique, we don't use the training data. So input is just, in this case, a random weight, just like a noise. Then we iteratively update and get this kind of image similar to the target image. The idea behind this one is the difference of learning curve. So that is specific to the, coming from the structure of the deep neural network. So this represents the learning curves for each image. So MLC versus iteration. So this one, is the learning curve for this image. So this one is a bit noisy one, but still like this. But other twos are just like noise. So you can see the difference, large difference of the behaviors of the learning curves. So that means that if we stop, so around here, so this image is restored. We can recover this image, but the noisy part not. So that's why if we appropriately set up the iteration point, that is stopping point, then if we exploit the difference of learning curves, then we can denoise, for example. In other words, we can say the network has high impedance to noise and low impedance to signal. Yeah, so same one. So this technique is used to like denoising. Well, it's hard, but ground truth and also the DIP. You can see the denoising, but also the in-painting, like the removing this kind of the effects of the in-painting, but we can remove, and also super resolution. So let's see the effects of the DIP in wireless communications. So I don't mention in detail, but if you are interested in, so domestic one we presented, it's not correct. So oh, maybe it's correct. So in this RCS technical report, but some others now under review, so I don't know detail, but we apply DIP technique for MIMO BP detection. Then, for example, that this is an uncorrelated channel, and then let's see, these two lines for without DIP. But if we apply the DIP, so because of denoising, then we can remove improve the performance. Also the correlated case as well. So DIP, so they now attracting more and more attention in even wireless communication field or signal processing. And also the super resolution. So we apply also some other papers, also focusing on the super resolution technique in wireless communication. Super resolution very popular in other fields, even the broadcast areas. And we apply the super resolution to this kind of the wireless communication, particularly the millimeter wave communication. Millimeter wave, so also introduced in the first keynote today. So very important. So I mean a new frequency band, and also that we can expect the larger bandwidth, and that means we can expect the high the data rate. So in that case, millimeter wave when we use, so in order to achieve to overcome the effects of the attenuation, then we need to use the beam, like a beam steering or beam forming. But for example, in order to select the appropriate beam, narrow beam, then we need to search very large space. And also they need a lot of the feedback. It costs. Then there are several techniques proposed to reduce the beam search overhead, like hierarchical search. First, just roughly estimate the direction. Then after that, in that direction, narrow beam we search. But still, the beam overhead is large. Then we apply the super resolution technique to reduce the beam search overhead in millimeter wave communications. The idea is like this. So for example, if we use this kind of the code book and then we get this kind of the low resolution image or beam domain image, like a 4x4, well, we represent this information by image, then apply the super resolution technique to get this kind of the high resolution image. Then this one, it corresponds to 8 by 8 DFT beam. That is a narrow beam information we can get just by using this kind of the low beam the search. That's why we can reduce the beam search overhead by using the super resolution. And also that we apply the kind of the DNN-based prediction because in wireless communication, channel is dynamically changing. That's why we need to apply this kind of the prediction technique. So I'll skip some parts, but let's see the performance, how much we can achieve. For example, this one represents the CDF of SINR by in a millimeter wave communication scenario and also the vehicular scenario. So about the details, so please see this paper, TBT paper. Yeah, of course, if we don't care about the search time, exhaustive is good. So this red one performs the best. But if we use the super resolution, then we can reduce the overhead. For example, in this case, the exhaustive search, like just the beam search, number of beam searches is 64, but the proposed technique is just 1/8. Then, but the CDF of SINR distribution almost the same. So that's one way how to use the super resolution in wireless communication that we propose. Okay, also in wireless communications or wireless networks, transfer learning also attracting much attention. Of course, in deep learning or other field, transfer learning attracts a lot of attention for many, many years. So how and why transfer learning attracts attention also in wireless communication? Okay, let's see. So, traditional machine learning tasks assume the training and test data are drawn from the same data space and the same distribution. But in practical case, we have to worry about insufficient level data. Well, sometimes it's difficult to obtain, or sometimes it costs. And this results in the poor prediction performance. Well, so that's why we need something. And also if we start from the scratch, that means that to train the model, it's always time consuming. That's also not good, particularly if we want to use this kind of technique in dynamically changing environment. So the idea of transfer learning is transfer knowledge from other sources. Let's see how it works. Okay, so just a definition. Yeah, I'll introduce briefly. Okay, notation just two, but the domain D, just a data space and the model as marginal distribution of P of X, and the task T, and the other space Y, and try to learn a function, mapping function mapping X to Y to appropriate underline the conditional probability P of Y given X. This is the general definition of domain and task. And here is the traditional machine learning. So in traditional machine learning, source domain and target domain the term, or also the running task and running task in source domain and tiny task domain are the same. But in transfer running, we transfer from the source domain to target domain. For example, then we can consider source domain is not equal to target domain, and or running task is not equal to running task. I mean source domain, the target domain. So this is an example. So source domain, target domain. So that those are the different. So like this one. So the first case domain, the first domain is like a kind of the web document one, target domain to web document, but different ones. Or source domain is text, but target domain is pictures, or target domain, source domain is illustration, or target domain is pictures, and also the both pictures, but are different. But we want to transfer. Then we want to exploit the information in other domain. In such a case, so the knowledge we want to transfer, but what to transfer? So there are several, like instant transfer, that is the data itself. Also the feature transfer, as the name mentions, we transfer features, or so it often used like a model transfer, parameters or priors of models, like a federated learning. So those transferred. So important thing is we need to consider is when to transfer. So when there exists relatedness between source and target domain, it's okay to transfer. Well, it's hard to say it's difficult to say quantitatively, but in general, we can say like this one. That means transferring knowledge from unrelated domain, it's not good. It can be harmful. So this is called negative transfer. So we have to consider from what we transfer to what. And also related to this one, meta-learning is also the attracting attention in wireless communication. So the motivations are the same as the transfer learning. So meta-learning itself, it represents the learning to learn. So then there are several papers including us. So I introduced briefly. So this is the one, so the transfer learning and meta-learning based fast downlink beamforming adaptations. So as the name mentions, so beamforming adaptation, transfer the knowledge from the other domain. So the system model is like this, multiple inputs, single output downlink transmission system, and K-single antenna users are served by BS with M antennas. So then we try to solve this SIN balancing problem. I don't go into detail, but this is the beamforming scenario, the downlink beamforming problem setting. Let's see the performance. So the SINR versus transmit power, and this is indoor case, and red one is a kind of the upper bound, so optimal solution. So this blue line, BNN, is like we have the data, I mean available data set in the same environment. So the training and the testing, so the data set are from the same environment. So then, of course, the blue one performs good. And the black one is meta-learning. And also this purple one, lower one, is transfer learning. So in this case, so our available data is different, so not exactly the same. Also, the amount of data is limited, but still achieve close to the best performance. And this one, downlink CSI feedback algorithm with deep transfer learning for FDD massive MIMO system. This is one of our papers related to transfer learning. Transfer learning also we proposed the published modulation classification. So just I mentioned some contribution of this paper. So like you can find which part we better use, or we had better transfer, or which part or which layers we better fine tune. We how can I say, clarify, and also to solve the problem of data set, we propose model agnostic meta learning. So I don't mention the performance, but if you are interested in, please refer to this one. So if we consider the problem, as I mentioned before, the limitation of data set, also the limitation of the training cost or time cost, and if we need to consider the dynamic environment, this kind of technique is very, useful, I guess. Okay, it's almost at the same time, so I will summarize my keynote talk. So the AI is a key enabler, or I should say one of the key enablers of 6C. Not all, this is not all, but it has a great potential for addressing big data issues. Also that, as I mentioned, in 6C, we need to achieve the very high performance in various aspects. And particularly the challenging part is the system itself or channel itself is complex and dynamic. Then applying the machine learning or DL, also the very challenging. Of course, there are many techniques to solve, but still ongoing. So there are many rooms to do research. So also the knowledge about AI becomes essential, even people for communication fields. So it's hard for me, but I'll try. And also the important thing that I wanna say again is AI is of course very good, and it needs data, but we need not just AI, but this kind of the traditional theory. We need to combine and use those effectively, then can achieve the good performance. Okay, so that's the end of my talk. So thank you very much. So if you have any question or comments, so please. Thank you very much.
Thank you, Professor Ohtsuki.
Thank you.
Now the session is open for you, the participants. If you have any questions, please ask or use the Q&A tab at the bottom of your Zoom window. Or just say, you may use the chat, I don't know. Or raise your hand. Any questions? Okay, I do have one question. Well, actually, I do have two questions, but I said it for the other time. Let me ask you one thing. Does the machine learning approach only give a suboptimal solution, or do we get the optimal performance somehow using the DNN or some machine learning?
Well, so it has to say the definition of depends on the definition of the optimum, but also depending on the first we need, for example, the in general data, even transfer or something, but still need data, and then in general So like not mathematically proved, I mean, we can achieve the good performance, but it's hard to say, so it is the optimal. Well, maybe some other specialists say so. But yeah, because as I mentioned, in general, so the many modeling or approximation, as the name mentions, it contains some errors or some approximated part. Then even if we apply some traditional optimum approach, we cannot get the best performance or optimum performance. But yeah, depending on we have the enough data and enough, it represents the, how can I say, diversity of the data itself, then there's a possibility, but still very hard because structure itself, there are so many, I mean, degree of freedom, also the tuning part. Ideally, there may be a possibility, but in practice, so of course, we cannot say we achieve this is the, I mean, optimal. It's different from a mathematical problem, so I guess so. Yeah, I also want to hear opinion about it, but anyway.
Okay, thank you. Any questions from the floor? Don't be shy. Okay, then let me ask you the another questions about the latency. You mentioned that beyond 5G and 6G, you are targeting the 0.1 milliseconds or less. How the performance would be in terms of the latency using the machine learning approach? Do you get the good latency using the machine learning or?
Well, there are many, so it's hard to say in general. For example, the environment doesn't change. And if we train the model and training data and test data or environment are the same, then once we train the model offline, and if we apply it, I mean, the test environment, then the environment are the same. Of course, we can reduce a lot. So that means the latency we can reduce. But in wireless communication, sometimes, well, maybe we can expect such kind of the environment, but dynamically changing, like a moving scenario or something. In such a case, we need to change. That's why, as I introduced transfer learning and also the not freely, I mean the trained model, but only because I didn't mention, but layers. So the early layers, so capture the fundamental part of the environment or the system. Then the latter part usually represent the environment dependent performance. Then if we tune like not full, but only some latter part of the layers, then we can achieve the good performance even in dynamic environment. In such a case, just a small amount of training data, I mean the test data, and also the small amount of the training time is good. Then we can reduce. If we apply so the fully, I mean the learned model, then of course the training is yeah takes time and not practical. We cannot achieve the such low latency. But yeah, there is a possibility that as I mentioned, but depends on the environment or the model.
Thank you. Any questions from the floor?
In the chat.
Yes. In some cases, traditional approach is better than using AI. Do you have some idea how to select which approach is good for a problem?
Yeah, good, good question. So in general, it's related to what I mentioned when or why we have to use AI or ML. So if we can model the system, I mean, very accurately, or our approximation is good enough, then just use the traditional signal processing or theoretical approach. That's fine. But in some cases, as I mentioned, so there is a gap. I mean, model mismatch or something, or suboptimal sub-approximation or accuracy is not good. Then even if we apply the traditional, not the traditional, but signal processing or mathematical technique, so there is a limitation. In such a case, so some cases, depending on the problem setting, also depending on the available data set, then there is a possibility we can overcome. So then, because for example, depending on the structure of the deep neural network, so then, yeah, in terms of the function, so we can represent much more, I mean, complex system. I mean, not mathematical, but model itself can represent or model. Then there is a chance to more fitting to this problem. Then, so the selection is, so first the accuracy modeling and also the available data set and those kind of things, then we'd better select. Yeah, of course, also the related to Professor Yamada's question before. So some techniques, so many parts we can do it offline, but some parts we need to do online. Then a requirement of the latency we can satisfy, or some other requirement, it's okay. Then some cases we use AI. So then those kind of things we consider them need to select. I don't say so. We'd better use always AI. So as I mentioned, so the signal processing communication theory or even AI should be based on those kind of the theory. So that's a kind of the selection criteria, I guess. So. Thank you. Thank you, Professor Bandai.
Any other questions? Okay, then I would like to thank the Professor Ohtsuki. Thank you very much. And please join me to thank Professor Ohtsuki. Thank you
very much. ありがとうございます。